Welcome to my video lesson. I gave it the title Fractional Calculus. It turned out to be a rather lengthy one. This is the consequence of the fact that I decided not to serve you separate courses, but to serve you the whole menu in one go, and leave it to your own leisure to stop the video at your own convenience. Fractional calculus. We're going to study expressions like the nth derivative of a function fx. If this n is an integer, positive integer, we read it as simply the first differential, second differential, etc., etc. For negative values of n, minus 1, minus 2, etc., we read it as the integral. Now, the question puts itself forward, can we extend this notion in a consistent way that we can interpret an expression like this also for fractional values of n? That I will refer to as fractional calculus. Already here we see an asymmetry happening. For the derivatives, a derivative is always unique and local. It tells you the slope in a point, or the deflection in a point. On the other hand, an integral is, first of all, non-local. The whole function weighs in on the whole interval from, let's say, x0 to the value x, but also non-unique, because this x0 has some liberty in choosing which value you choose there. We will see that as we extend our notion about differential calculus, also for non-integer values of n, the derivative starts to be non-unique and non-local, but we're getting ahead of ourselves. Why should we care about this? First of all, there's of course the mathematical interest, but that was not our primary drive. Our holy grail in this case was the Lagrangian formulation and the principle of extremal action, and the possibility if we could include a kind of dissipative term into this Lagrangian. So we're looking for a Lagrangian with terms in it, so if we simply apply the variational principle, it gives us a term proportional to the first derivative of the variable to time, simply from the variational principle. To obtain this equation of motions, already concepts exist. For example, to use a Lagrangian which is time dependent. Or use auxiliary variables. I find it hard to, using these principles, to reconcile the relations between the momentum and the Hamiltonian. That makes me a bit skeptical. The problem is, already in 1931, Bauer proved that it was impossible to formulate such a Lagrangian. And his argument is sound. Looking at his proof, he leaves a loophole. And the loophole actually is that he only considered integer derivatives. So we could circumvent this by looking at non-integer derivatives. But how do we interpret them? Riewe already showed that if the Lagrangian contains the nth derivative of a variable 2 times squared, then the corresponding variational principle would result in an Euler-Lagrange equation which contains only the 2nth derivative of the variable. So if you want to have a term which is proportional to the first derivative of time, our Lagrangian should contain a term which is the half derivative of that variable to time. That is 1. What we will show later on is that this half derivative starts to be non-local. So the fractional derivatives are non-local and unique, similar to integrals. The whole process tells us that the whole function will weigh in to determine this variable. And in a sense, this is exactly what you want from a dissipative force. The previous history has to account for something. So also on this footing, this seems like an interesting approach. Only the integer derivatives truncate to local, not the half derivatives. So far, so good. Let's see if we can wrap our heads around what such half a derivative would imply. And let's start with a kind of duct tape solution. Okay, let's enforce that the differential of the exponent still reproduces the exponent. So that means at least for integer values. And let's assume that it still holds for fractional values, where gamma can be any fraction. That would mean if we look at the fractional derivative of the cosine, which can be interpreted as the sum of two exponentials, can be actually calculated. Now we realize that actually this imaginary number is also an exponent. So this fraction turns out to be, and what we actually found is that the fractional differential of the cosine just simply gave us a phase shift of gamma times p over 2. Once we did the exponent, for any function with which a Fourier transform exists, as is written here, we now know how to calculate this fractional derivative. That would be simply this. So far, so good. But what now if we take a function for which the Fourier transform does not exist that easy? For example, the function fx equals x. This function is open-ended, and so no straightforward Fourier transform exists. But then we realize that the Fourier transform is not the only expansion we have. For a large class of functions, we can also use a power series expansion. Let's see if we can use the same trickery as before for this power series expansion. So let's take a power function. Then the first derivative looks like this. The second like this. The third like this. And now let's simply generalize it. Be careful, we use the fact that the factorial function for m minus n, as m minus n starts to be negative, has an absolute value of infinity. So that term automatically turns 0. Now we generalize it for n not being integer. That means we have to change the factorial function for the gamma function. and we get notice how nice this works. If we take, for example, n to be -1, we get so this notion also captures integration, which is a nice thing. This is nice. Voila. Why is it so nice? Actually, what we get is that both the power series approach as the Fourier transform approach reproduce the inverse relation between differentiating and integration. So that means if we take the gamma's derivative of the minus gamma's derivative, that means integration, we reproduce the identity operator. But again, remember, this is only a duct tape approach. Huh? And with all duct tape approaches, of course there will be some problems ahead. You only have to figure out what are the problems. What is the snake in our paradise here? Let's look at our expression somewhat closer. Let's start off with our power series notion. This is what we derived before. And now determine the half derivative of simply a constant. That would give us, by that formula, this is a kind of surprising result, particularly because it's infinite at x equals 0. But okay, it be as it may. Then we realize that actually our exponential can be expressed as a power series. That means we can use both approaches, determine the half derivative using the Fourier transform approach, and determine the half derivative using the power series approach. So the Fourier transform approach would give us, and the power series approach would give us, these are two different expressions. And if we plot them, that is even more striking. Well, that's the picture again. Clearly something is wrong here. Does that mean we have to give up this nice notion for the derivatives of the exponential, wherein the gamma derivatives of a cosine just gave us a phase shift? The answer to this is no, and the reason for this is that derivatives, especially the non-integer derivatives, because the integer derivatives will truncate, are non-local. and non-unique. To see this, consider for a moment the following two anti-differentiations. That means if we want the first derivative of 1/4 times x to the power 4 to be x equals x to the power 3, we have to choose x0 equals to 0. Whereas if we want the derivative of the exponential just simply be the exponential, we have to choose x0 equals minus infinity. That's where the subtlety lies. So what that shows us is that a more fundamental approach is needed. Let's first try to get a sense of what we need. By definition, the first differentiation is defined as let's differentiate it again. That would give us notice please the subtle play of limits that is played here. Now rearranging the terms, see how almost by nature the binomial coefficients reappear in our expression. If we would even take the third derivative, we would get and again the binomial coefficients reappear 1, 3, 3, 1. We recognize a pattern in this. It's quite easy to see that the nth derivative of our function fx would be something like this. Okay, how do we interpret this? Let's look again at our second derivative and using our formula. That would give us, just following the formula, and now we do something to it. We're going to add terms of f in the point x minus 3 epsilon, in the points x minus 4 epsilon, x minus 5 epsilon, etc., etc. Only the coefficients in front of it we set to 0, like this. And then we state that for as long as n is integer, the series will truncate. For n equals 2, the series truncated at x minus 2 epsilon. And all the other coefficients are turned to 0. If we now take the limit of epsilon going to 0, it turns out that only the values infinitely close to fx will contribute to this series. And that makes our differential local. The statement now will be that as we take a fractional derivative, these coefficients will no longer be 0. And all the values of f between x and x0 will contribute to the series. And that makes our fractional derivative non-local to start off with, but also not unique because you chose an x0. but we are getting ahead of ourselves. Okay, where do we stand? We found a generalized expression for the nth derivative of a function fx, for n being an integer. Let's be clear here. Now what we want to do is extend this definition to also include fractionals and negative numbers. Immediately two questions pop to mind. First of all, what do we do with the binomial coefficients? It's clear that will involve some kind of gamma function. And the second point is, what do we do with the upper bound n of our sum? To answer this, we will start off from scratch. Okay, we start off with an arbitrary smooth function on the interval x0 to x. Voila, there we go. We divide this interval in pieces epsilon. In this case, 1, 2, 3, 4 pieces. And we introduce what we will call a shift operator. A shift operator operating on the function f, x, will give us back the value of f in the point x minus epsilon. Now we introduce the general operator d as such. Notice that if we take n as 1 in the definition, we nicely get the differential operation. And notice if we take n equals minus 1, we actually get an integration. And now we use the fact that 1 divided by 1 minus our shift operator is actually the outcome of the sum from 0 to infinity of the shift operator to the power n. So what we get now is this. And actually this we recognize as an integration. See how this also works for our second derivative. Now we use the binomial theorem. That actually is our previous expression. Seems to work like a charm. Let us generalize this even a bit more. What we learn up to now is that we can read the nth derivative as follows. Now we apply the binomium of Newton for the power n term. Take out the minus 1 and use the fact that our sigma term is just a shift operator. And now comes the magic. We shift the upper boundary not to n, but to x minus x0 divided by epsilon. What we actually did is that for integer x, the summation truncates as soon as j exceeds n. To see this, realize that n over j is actually this. And n minus j factorial, these absolute values, goes to infinity as soon as n minus j is smaller than 0. it is this red equation which we will use as a definition. So we define our nth derivative of the function f by this expression. Notice the upper bound of the sum. And we are using the fact here that for integer values of n, this series truncates, because n over j equals 0 for j exceeding n. So for our second derivative of f, using this expression, we indeed get what we previously pointed out. All the terms are included, only some terms have a 0 in front of them. And as epsilon goes to 0, only the values of x, f, close to x, will contribute. But that's only true for integer values of n. Now it's time to generalize, to extend the notion also to fractional powers of n. Taking our previous expression, only now allowing for fractional values, that's why we use a gamma, we would define the gamma's derivative of f as follows. The last step is how to interpret gamma over j. Well, let's look at what it meant as n was an integer. So we need to change the factorial function into the gamma function. The gamma function lets us allow to calculate the factorial of fractions. How was it defined again? So gamma over j now simply means there you have it. Summing up, we define the gamma derivative of a function f, and gamma is now allowed to be non-integer and even negative, as the following expression. What is completely analogous to this one, realizing that epsilon is actually the spacing between x0 and x divided by the number of pieces we broke it into, is this one. Same expression, only written in a different format. Realize this expression for arbitrary gamma is non-local, because all the functions from x0 to x weigh in here. And only if gamma is an integer, this series truncates, making the derivative local. Furthermore, the expression is non-unique because we chose a particular value of x0, like we did for integrals. To express this, we introduce the following notation. Okay, so far so good. Let's take this expression and look what happens if we consider a negative integer. So let's write it as follows. The problem now is that this binomial expression doesn't work anymore, because for negative integers, the absolute value of the gamma function will turn out to be infinite. This cannot be, because we already saw with our shifting operator that it should give us a nice integral. So this is an artifact. So let's rearrange this binomial expression. This is actually its definition. Now change the summation of the product of L over the product of minus L. Take out the minus And this is our new expression. So the two minuses in our definition of the integral cancel. So for negative values, negative integer values of n, we get and again realize this is simply an artifact. Doing the same trickery again, instead of epsilon writing x minus x0 divided by n, we also could have written this as now it seems like we got everything under control. To get our bearings, let's play around a bit. First of all, let's choose in this expression n equals 1 and see if that actually gives us back our integral. So taking our expression, filling in n equals 1, the gamma function of 1 plus j is actually j factorial. The two factorials cancel out. We change the summation in integration. Now we shift variables. And then we realize that x minus n epsilon is actually x minus x0. And we've got it. So far, so good. Second test. Can we reproduce the results we found for the exponential function? For this, it is important that we realize that this expression is non-local and not unique. Again, what do we want to reproduce? We already realized to get this, we have to set x0 equal to minus infinity. So what we need to calculate is this. There we go. Our expression. Then we take the e to the power ax in front of it. Then we realize what is actually between brackets is the binomial. Then we realize that for the exponent we can use a power series expansion. So this. Now letting epsilon go to 0, what we're left with is actually this, the result we wanted. So far so good. The next thing we want to do is reproduce the power series expression. So we want to reproduce this one. We already realized that for this we had to set x0 equals to 0. So we have to calculate this expression. There we go. Now we put the m in front of everything. That will give us and with some effort you can show that what is behind the limit actually is the same as this term, but it is only with some effort. So indeed, it also reproduces what we expected. Not easily, but it did. So summing up, we found that it was possible to make a consistent extension of the definition of a differential also for fractional values. our first form was. That is including the epsilon. And in our second representation, we didn't use epsilon, but x minus x0 divided by n. That's this one. Where our binomial coefficients were actually defined as in terms of the gamma function. This was not an easy expression to evaluate for negative values and integer values of gamma. The reason being that the gamma function, gamma plus 1, exploded. So we rearranged it to form the following expression. First the epsilon variant, and then the n variant. So we know it exists. That's first. And that for fractional non-integer values, it's actually non-local. All the values of f in the range from x0 to x are included. Furthermore, it was non-unique. We had to choose a value for x0. It's only for the integer values of the gamma that it turned out to be local derivatives. Because then all the series truncates, and only the values of f close to fx contribute to the series. Furthermore, it was unique. We have no problems anymore with our x0. So we convinced ourselves that these fractional derivatives actually exist, but they are not always easily calculated. What showed that was that when we tried to reproduce the power series expression, we got in a hell of a mess. We could do it, but it was not easy. Is there some way we can make our lives easier? Actually, it turns out to be, the answer to this to be yes. Watch this trick. Instead of looking at differentials, we are going to look at integrations actually. So consider to the power minus 1. That will give us this. So twice integrating would give us an expression like so. What we now do is change the order of integration. Notice in red the change in boundaries for the integrals. We come back to that in a moment. And this integral is actually doable. Now, what about these boundaries, these red numbers? First of all, realize our function is only a function of t1. We got two variables, t1 and t2. What actually the red expression tells us is take a value of t2 and integrate over t1, like so. Then take the next value of t2, do the same, do the same, do the same. We're going in a horizontal direction. Now, instead of horizontally, what interchanging dt1 and dt2 did is cause us to go vertically. Like so. That's how we get to those red boundaries. The next step will be again to generalize this expression. So n times integration would give us this. That's for n being an integer. That means for n being factorial, fraction, that will be this. However, notice that this only works for gamma being positive. Otherwise, our integration will diverge. Question puts itself forward, how can this help us? Well, consider this. To calculate the fractional derivative of f, we of course could differentiate it one time and then integrate it half a time. So that means this. And now we can write suppose now we would apply this formula to our original function f of x equal x. That would give us this would actually be the answer. Phew, there was a lengthy story. I hope you're still with me. The only thing that's left of me is to thank you for your patience and your endurance. Signing off, Urs wieder.